Hello, everyone. This is Roger, and I'm online here with Jörg Feldman and Andrew Feldman, and we're going to go through an introduction to concepts that you need to understand in order to be able to interpret data from the Moxy. So we have a PowerPoint here that Jörg has put together, and the three of us are going to discuss this as we go. So I'm going to hand this over to Jörg Feldman, and he's going to jump in with his PowerPoint.
Okay, thanks together, and thanks for the chance to give us here to try to explain some crazy ideas we developed, but as more and more we discuss with people, we realize they're maybe not that crazy, but there still needs some clarification on why we do what we show you on the Moxy forum or in individual presentations. So you may see in front of you a very simple wording, tip, rip, and zip, and I assume you see that. These are words we just throw around and we just developed to not confuse with other current testing or assessment system. It's basically, tip would mean it's a training intensity profile. So we use Moxy now, and we will see later why we use it that way, to find out individually how your athlete or your client or yourself may have to train when you do an endurance training. So we find what people name zoning, but on an individual base. RIP would be the same idea, but for sports like ice hockey or team sports, where we most often have situations where the athletes either go all out or very little activity. And ZIP would stand for people who do fitness training for strength, individual profiling. So these are just three words. They may show up once in a while, and we try to explain you that why we developed that and how that comes up. So basically, Andre and I try to present you a whole bunch of information we gathered together over many years. And the whole idea is very simple. We try to close a gap between what we do at the university in a science lab or in high-tech training centers where people get hooked up to many hoses and cables. And we would like to show you that this is great and it still should be done, but it's potentially for many coaches out there practically not applicable and you can't use it really. So we like to show really hand in hand how we can use high-tech science equipment and use it practically in the free world. So that the two pictures really for me present these two worlds. The one athlete who goes in the lab and everybody looks in whatever hole he can look into and find all different kinds of information. And it's maybe very painful, but when he leaves the lab, there is very little the coach and the athlete can do with the information they find. So this is what I mean closing the gap between the science world and you guys out in the field. And Moxy may be one of the tools you have to consider. So when we actually ask the questions, where do we start from here? So this is one of the main problems. Where do we start? Because it's a huge field and information I gathered over the last 30 years. So the main approach would be, and I put that in very short words down here, we like to show you that what you see on interpretations on the forum or what we explain on interpretations, we see from reactions like the total hemoglobin on the SMO2, it's not something we suck out of the air. It is something we collected with many, many different tools and are quite sure that in many cases what we actually see with Moxy interpretation can be backed up with these more expensive tools. That you actually can follow that, you have one big problem. You have to take your brain out of the box and you may have to help us to think outside the box here. So we have a big challenge. We have a very small equipment, a Moxy, where we do physiological assessments and try to get physiological ideas out, and you fight again a classical physical testing tradition where we just have to have VO2 max, we have to take blood, and so on. And we like to show you that perhaps we need that and we can combine it, but for many people it may be possible that a lot of the information from the classical physiological testing can be found when you look a bit closer into what Moxy can tell you. So this would be the challenge we put out here. So the basic discussion in exercise physiology is potentially that something in the development of exercise physiology, when we go far back to the 1800s to today, something obviously went in a very different direction. From an overall picture how physiological bodies work, so from the idea about survival or fight and flight, the high-tech physiological exercise information goes much more into microbiology and specialized in many, many subcategories, which is not negative and may be very interesting, but in many cases it's not applicable for people like you and me who do sport and like to work with people. So the question is whether we have to make a step backwards from our sitting job to perhaps the fight and flight job. And this is where the whole Moxy idea comes back into action.
Jörg, can I quickly add something? One of the points that I always like to add to people is when we take that step back, is to think that athletics and sport is a pretty modern concept if we look at the human species. So before we had athletics and sport, the reason we did high-intensity exercise was usually out of survival reasons, so either to get away from predators or to chase prey. So I feel if you take the aspect that sports is really almost like a modern day equivalent of this kind of hunting, surviving environment. So really what we do and how we do athletics and how the reason we get tired or the reason we have a certain level of performance is an evolutionary based reason. And you need to look at it, from my opinion, from that view as well. The idea that sports is really only a modern concept, and the way that we react to athletic stimulus is really a fight and flight, evolutionary-based survival reaction.
I absolutely agree, and I think people who look over this weekend the CrossFit World Championship, they understand that survival we had to do, as Henri points it out, today gets actually moved in very extreme way how we load and overload people. And so that's why I think there is a very close relationship between what Henri just said on the survival and what we today see in absolutely extreme high performance sport. So basically what we did in the early days, we were looking at physiologically why do we function and what is the priority really when we function to actually survive that high performance sport, or for example that ability to work like Henri just put down there. And the question is, can that be found in what we mainly do with assessments? Can that be found in maximal wattage or power output, maximal VO2, maximal heart rate? And for sure the question is, can we actually use a computer finding one spot in whatever testing system we have, and then use percentage of these maximal values. And this will be a critical point. I think it's fair enough to discuss that critically and say, is that the way to go? Can we make a cookbook? Or is it so that it would be perhaps more valuable if we could do more individual assessments? And this is where I think for the moment many discussions start, and sometimes unfortunately we end up when we open that clear but critical question. On that,
if I could jump in here on that survival instinct, just for an example of how that manifests itself, just so people can think about it. And correct me if I'm wrong here, but one example would be the cardiovascular system works very hard to maintain blood pressure. It protects the body against sudden drops in blood pressure and has all kinds of mechanisms that do that. And that's one of the survival mechanisms, because if you lose your blood pressure, you'd quickly become unconscious, and that's not very desirable from a survivability perspective.
Exactly, and yeah.
So I think the easiest one actually to think about is temperature, because everyone knows what happens when you're outside and you get cold. Your fingers get numb first.
You guys are getting ahead because it will come.
Okay, there you go.
Yeah. So what I like to do first is I like to show you that everything we talk about here, it's not out from our brains. There are much bigger brains out there, and we fortunately can use a lot of these ideas and try to connect it all together in what we do. And one of the brains which often comes up is Archibald Hill's, and the whole discussion about VO2 max and all that started actually in his time, where he had incredible ability to make thoughts and theories based on thinking and not really having the tools to prove whether they're right. So whenever we take stuff over, we always have to think how far ahead of the time they were, but we also have to accept the fact that sometimes great ideas may change because the facts don't fit anymore in the theory because we have new equipments. And I think that's what we have now the advantage. We have an incredible development of new equipment. So Archibald Hill actually did something incredible. Besides believing that there is a maximal VO2, he actually realized that there are a lot of questions. And he used one interesting word in his theory. He named it a governor. And the governor for him was clearly there was somewhere in our body, most likely in the brain, a system which may control whatever we do over feedback loops. And another guy who took over many ideas from Archibald Hill's, Timothy Noakes, clearly uses that word governor to show that Hill was actually interested in the VO2, but he not had all the explanations to it. Therefore, he opened that option of a governor or central governor, as Noakes would tell us. Another guy who really influenced a lot on what we do in sport, but certainly also how we will use Moxy, was Hans Selye, an Austrian guy who moved to Canada, and he created the so-called GAS, the General Adaptation Syndrome. And I'd not like to go very far into that, but interesting in his case was that he believes that there has to be something out there who stresses us. The stress will disrupt where we feel comfortable, or so-called homeostasis. And that may change and allow us to make progress or perhaps not progress. And he clearly pointed out that to actually change this homeostasis, we not always have to overload, but we have to disrupt it. And for me, this is an important part in today's high-performance sport, because in high-performance sport, we just believe more, tougher, and harder. And sometimes we kill a lot of potential there by just overloading it instead of trying to disrupt it. And we can go then later in different webinars into that discussion, but that's just that you see where we're coming from. So the GAS ID, the General Adaptation Syndrome from Selye, had 3 phases. And in very simple terms, he had an alarm phase when you start out to do something. Then you may reach an adaptation. That means your body may react and try to react on that stress. And then you may actually go so hard that the homeostasis you try to reach get interrupted or destroyed. So simple is the heart rate to use as that. If you suddenly jump up and down, it's an alarm phase. It takes a little bit time and your heart rate will start to shoot up. It may actually overshoot because he thought you get nuts, but then you find the balance and your heart rate may stay on a higher level instead of by 60 resting heart rate, perhaps by 140. But if you keep going harder and harder, so you push more and more alarm phase, suddenly the homeostasis at 140 will be disrupted. You go higher till you basically fail to do any further activity. So this idea about these 3 phases is really what we do with Moxy. And this is an old picture where we used one of the first years we could use wireless was Portamon, but exactly the same picture will be done with Moxy, just on a much easier way. So what you see here is 2 values, and the yellow value is your SMO2. We use that now as a green color, and the purple value is, no, the purple value is your SMO2 and the yellow value is your total hemoglobin. For total hemoglobin, you normally use brown, and for SMO2, we use green. So you not even have to know the numbers, but just look what happened. An alarm phase, this is a specific test we did, and you can see, even if you have no clue what we did, that at the beginning, we have a whole bunch of phases where you see yellow and purple, so total hemoglobin and SMO2 go up. Then we have a clearly phase where you see there is a kind of a balance coming in, homeostasis, and you see this in both values again. And then when we keep pushing further, you have Celius disruption, homeostasis disruption, and you see that we have in both informations we can get from Moxy, total hemoglobin and SMO2, you can see a drop. So this is a simple example of an optimal load, creating a balance and unloading situation. And I like to show you why we believe we can see that and how we build that whole information on there. So the last guy I have to bring in, otherwise it doesn't work, is Walter Cannon, the father actually of the fight or flight ID. And here, very short summary on symptoms of fight and flight. You will create an increase in cardiac output. You will create an increase, therefore, in blood flow. You create an increase in ventilation over your respiration system. You will create a whole bunch of vasodilatations in your body to move blood to the area where it's needed, and you will increase your muscle activity. These are his 5 very basic reactions of a fight and flight. And what I put in behind is to show you how we try to find whether we can prove these reactions live as we do a test. So one of the equipment where we look the cardiac hemodynamic or the cardiac output is Physioflow, and we may be later going on that. Increased blood flow we can see over NIRS, Portamon we used, and now we use Moxy. Increased ventilation you can use over any kind of VO2 equipment you have. We mainly used FitMate and K4-2B because they were just great available for us, and the K4-2B was a portable equipment. We use information for vasodilatation, back again with near infrared, and increased muscle activity we use different surface EMG equipments. So you can see there is a huge amount of equipment involved, which costs quite a bit of money. If you go for the top equipment, you're far above $100,000. And we like to show you that the coach out there who just simply can't afford all that information, he also don't like that information and data overflow, may be actually able to move just down to a single simple equipment, and this would be for us the Moxy. So when we go one step further here, then this would be the summary of the equipment. And you can see what we use for what. So the extended central governor model would mean we were looking over a FitMate from Cosmed, how your lungs would work, over the Physioflow, how your heart reacts, over Portamon or NIRS or Moxy, how that finally shows up in your locomotor muscle. And then we used surface EMG because we were interested to see how they actually connect with each other. So this is really the lab, the complicated guy. But the idea is to bring you off the table into the field and actually work out with that. And now here we are, and that's what Andre actually started to try to explain. When we look about survival, even in today's time, the easiest way to explain survival is over temperature. If it is very cold outside and you decide to go basically out, and you're naked, you not immediately die. But your thermostat in your body, respectively your brain, will give you some information. Holy, it's a little bit too cold to go out in that temperature without clothes, and I actually like you. So I give you a chance to survive in the way that I try desperately to defend the core temperature. But unfortunately, because it was the stupid idea to go out and it was that cold, I have to give up some ideas to survive. And I will have to survive, make a vasoconstriction mainly and first in your extremity of your body, so that I can actually protect your vital organs in your system. So what will happen is you will get cold feet and you will freeze your feet, you will freeze your fingers, potentially your ears and nose, but if you're smart enough, you still may be able to sneak somehow back in the house and you survive. So we have a reaction controlled by the brain to help you to defend a vital part of your body, which is your core temperature. And I think nobody really would argue dramatically against that particular idea of survival. So when we make that a little bit more complicated now in sport, then we have a situation where you start to run, for example, and you run harder and harder and harder and harder. So like it would go colder and colder and colder. So what you have a much, much higher demand for energy, and the ultimate energy we look always for is the oxygen. So as the demand of oxygen goes dramatically up, you will start to get into a situation where you just may not be able to deliver the amount of oxygen needed for the speed you have to run for survival or for your race. So that means there is a danger showing up. And the danger is that I have to make a decision whether I can afford to move all that oxygen in my legs and arms when I actually have much more vital organs who can't afford to not have oxygen, which is, for example, your heart and your lungs. So obviously, again, we will have a feedback from the heart, from the lungs, to the brain that the PO2, the ability of taking oxygen that I can survive, may be getting low because somebody takes a lot of oxygen to run. And the brain may have to make a decision that to be able to survive, I cannot afford to send all that oxygen to whoever asked for that oxygen. And he has to make a decision, what is more important for you, to run around or to survive? And as for the most people, luckily the body says, well, I really don't care how fast you run, but you have to survive. It will create some reactions over vasoconstriction and muscle recruitment step, and that's exactly what happened and what we look with actually Moxy.
Jörg?
Yeah.
So explaining this to people, one of the questions I get often is if there's a central governor that with the goal of survival so that the athlete, in the case of an athlete, does not die during exercise, why are there still cases of spontaneous death in athletes during competitions? When someone asks a question like that to you, what response do you give them?
Well, the response is exactly that the feedback loop to the brain didn't work. So we know in many cases where we have sudden death that there were some medication involved who kill that natural barrier of protecting. So an average person like me, for example, I use perhaps 60% from my ability when I go all out, and then the discomfort is so much that I just think, well, this is more, and I quit. And with regular training and pushing, you most likely can increase the percentage of what you have. So your functional ability is the first thing you will improve when you go and train. So instead of using 60%, you may use now 70 or 80%. But what we know is that you never will use normally 100% when you just go out and push yourself. With, again, the exception of survival. And that's why you have these incredible survival stories where somebody was running with one leg shot off behind the enemy line to go in safety, or you have this incredible situation we just had lately, that surfer in Australia who fighted the shark who attacked him during the competition a few days ago. Or we had just 3 days ago here a surveyor who actually fighted off a grizzly bear, and when he got asked, how did you do that, he said, I don't know, I certainly had much more strength. That's where the central government says, you're dead anyway, so you fight, and whatever, if you're lucky, your vital organs will survive, and then you survive, and if you're dead anyway, because the grizzly bear will be hungry no matter how much you fight.
So basically we're looking, if we take it to a very practical and an approach that many people understand, and we go back to the CrossFit Games, how do you see then do you see that as really important that as a coach or as a trainer and also as an athlete that you understand the psychological surrounding that you're in? So if we take CrossFit, for example, and you get the rhabdomyolysis cases that are likely due to the large amount of peer pressure in a group that's pushing people into this kind of a dangerous area, and the understanding of that in this concept of a central governor, to understand how psychology plays a role?
I think that's a very, very good point, and I think for the moment here in Canada we see this with these incredible results. Many of the athletes doing the Pan Am Games from the really, really drive of pushing with more, so you can push a few percentage more. But exactly that problem with rhabdomyolysis and the CrossFit shows you how good the central governor is, because it kills muscles that you still can survive. So if that rhabdomyolysis stops you from actually working harder, at least you survived it. You killed some muscles, but you survived it, and you didn't actually attack your vital organs to actually keep going. But it shows how hard these guys can push, that they are able to destroy muscle tissue, and are lucky that they are very, very healthy, so that the central governor still is able to protect that particular area we need to survive.
Okay, good. Yeah, no, I just wanted to bring that in because I think that's an important point and a very contemporary one.
Yeah, and I think it's a point really worthwhile to discuss and to show why perhaps in a training you may not like to push every time that far as you may do it perhaps in an event where you really get highly motivated. But if you do this in training, that's where the training certainly may be destructive and not constructive. So you do catabolic workout and never have a chance to get an anabolic reaction back.
Yeah.
So basically, when we go back on that whole part, I put a very simple pyramid on here to make it easier. We have, as it looks, a hierarchy where we try to protect from the top to the bottom. So we need some oxygen, or we need some survival for the brain, that whole control can keep and take place. We need the heart and the lungs to keep moving, that actually the brain gets enough oxygen, but we really don't need too much of the muscles. So that would mean if I go harder and harder and harder, and I have a limitation of oxygenation, I may see that the extended central governor or the brain will stop actually moving oxygen and blood to your locomotor muscle to protect what we just discussed. And then we have an additional survival option down there in the way that I name it involved and non-involved muscles. So for example, when you run, the most people who run very hard realize that they actually certainly get stiff arms before they actually slow dramatically down. So we have a lot of research out there who shows that obviously the body, when you push very, very hard, can, even when you not anymore move oxygen to the locomotor muscle because you have to protect the vital organs, you seem to have the ability to shift blood from one body part to the other. So we see, and again we see this with Moxy surprisingly with NIRS, that you certainly reduce the blood flow in your arms or total hemoglobin, we can see this, and you see the drop in SMO2, less oxygen in your arms, but you still can maintain for a while, not much longer, but for a while, your ability to move and run the same speed because you shift oxygen from areas which are not needed to survive in areas which are desperately needed to survive. And this is what Roger explained with the blood pressure. So when an absolutely high top performance athlete trains over so many hours, these Tour de France riders or these extreme triathlon guys, they train their muscular system incredible. So they have an incredible vascularization, meaning many meters of blood vessels. They have a lot of mitochondria, meaning a lot of areas they can use oxygen and convert oxygen into energy. And they may have developed that system so incredible great that the cardiac system is not able to move that much blood in all the blood vessels which are open during an all-out event. So if all blood vessels stay open, then the heart itself has not enough power to maintain the pressure in the brain, and so the brain has to make a decision to close some areas which is not needed, vasoconstriction, to maintain the blood pressure to survive. So this is an excellent example, and for us the beauty was, after many years of searching, can we prove that? We think we can show that now live as you actually do sport by looking on trends from total hemoglobin and SMO2 with the NIRS. So this is what that pyramid is, and this is where the whole NIRS sets up. So now again, we didn't suck that out and saw NIRS graphic. And for me, a NIRS graphic at the beginning is like somebody who never works with a echocardiogram. When you see the first time the up and downs from your heart, you have no clue what that means. But many great brains finally made basically a mapping out of that, and each peak and each valley means something. And for us, the same happens with total hemoglobin and SMO2, that as longer we work with this and as more we combine that, as more trends going up or down started to give an information to us. And this is what we like to show you with NIRS and with all these informations we do. So when we go back to that, to the whole idea, when we look at the body, I made a simple picture here, and everybody knows that you have a respiratory system, you have a cardiac system, you have a transportation system, you have a utilization system, and a release system. And each of these systems actually can be tracked down when we use NIRS. So I just make a very simple example for everything. The respiratory system mainly is looked upon on that I get oxygen in. What we often forget is that it is at least as important to actually get the CO2 out. And CO2 is a very potent substance to create reaction in our body. And one of the reactions when the CO2 is very, very high, because we can't release it, is that we create a dramatically big vasodilatation. We can see this over total hemoglobin reactions. Another thing CO2 is doing, it shifts something, and for some it may be a strange word, oxygen dissociation curve to the right side. In simple terms, CO2 makes your oxygen less sticky or more sticky on your hemoglobin. So if you have a very, very high CO2 level, then your oxygen is not very sticky on the hemoglobin, and it can be very easy released to be used in your muscle cell. That is short-term a very, very important survival idea, because you for the moment not may get oxygen in. Because if the oxygen is much less sticky, then you have a problem to load it actually from the lungs to the blood. So we can see that again when we look at the trends of SMO2, and I don't like to go much deeper into that, but that's just an example how we can see how the respiratory system works by looking at total hemoglobin and SMO2. We can also look at utilization, and that's where we mainly look at SMO2. So normally when we see live SMO2 drops, then we know your body uses nicely the oxygen, and it uses it so good that you use it more than you for the moment deliver. So a drop in SMO2 is a clear indication for us in many cases that you use oxygen but you don't deliver enough. Another example is on the right side, the respiratory system, and I explained it. It can be a release system, but it can be also an intake system. So total hemoglobin can react nicely when the respiratory system itself gets into limitation, or when it's a limitation that you have so much blood vessels that you don't get enough oxygen. So that would be something we can discuss later over the metabolic reflex. Then we have the cardio system, which is very clear for most of the people that if the cardio system starts to work harder, meaning if your heart rate, and that's something we can always easily read, if your heart rate goes up, you most likely also create a vasodilatation and total hemoglobin can go up. There is more information there. We can see later why we see that, because we looked not just heart rate, but we looked also at stroke volume. So last but not least is the transportation system. So if you have many blood vessels, you will see that total hemoglobin can go much more up. If you have not as many blood vessels, you will see that total hemoglobin not will go as much up when you start working out compared to your start level of total hemoglobin. The other thing is also the transportation system, so the blood vessels react very nicely of contraction and relaxation. That means when you make a muscle contraction, like for example a biceps curl, but not very hard, you will see that total hemoglobin will drop, and we will show examples. If you push harder, then you may actually push so hard that your muscle compression will not allow any more outflow of blood, so total hemoglobin can go up. And then you have a situation where you may see total hemoglobin doesn't change at all when you do a very, very super hard contraction and you create something like an occlusion, which is a lot of discussion going on in strength training. But again, this is just an overview to show you how we use the simple information of total hemoglobin SMO2 to evaluate the different system, and the key is to figure out how they interact with each other. So
I want to add one more point there. You talked about how you want to bring together basically application or practical work with the academic side, the scientific side, and that there's that disconnect. And I also feel here that at times there's a disconnect between within the academic side itself. So what you're basically doing here is when you talk about respiration and potential respiratory limitations and the effect of the respiratory system, we're talking a lot about the Dempsey's metabolic reflex. So Jerome Dempsey's metabolic reflex. And then when we're looking at the cardiac system as a limitation, we often talk then about the central governor and Timothy Nowak's. But what's interesting is that they both discuss very similar concepts for different physiological systems, but at least from my knowledge, I've never seen an overlap where they say, hey, well, basically, it's the same thing is happening just with a different system. We're really talking about a same kind of a reflex, a survival instinct reflex. And that's where I feel that the scientific community at times doesn't work in an idea to bring something together for a practical approach. They just do their own research, but to realize that these pieces actually fit together and can be used in practice is lost often, at least how I feel.
Yeah, and I think that's exactly the answer we see on that picture. When you look at under each of the circulation, you see some really great researcher names who are all researching and do incredible work in their particular field. But as Andrew points out, as a coach, I don't have an athlete who only has a heart. He luckily also has some legs. And I have an athlete who also will breathe. And this is a beautiful picture out of a nice presentation Holmberg did from Östersund. And I love that picture because it is one of the confirmation for us, for Andre and me, who work since many years on that we believe it is an overall approach, and I will show that later with the team approach and our rowing idea here. But yes, that's exactly, I think, what the point Andre makes is the point I always get kind of confused when I discuss with top guys how narrow-minded they look at their field. And yes, they are perfect in their field, but as a coach, it doesn't help me a lot if he only looks at the heart and doesn't realize that the heart has some connection to a whole bunch of other organs.
Okay, Jörg, I'm gonna jump in here. Our time is just about up here for this session. So thanks so much for doing this great summary. And then we're going to move on and record some additional sessions that go into some more specifics about how to apply this introductory knowledge. So thanks so much for presenting this session, and we ask everyone to join us for some follow-on sessions that go into more detail.